You know, you use it literally every single day, but you've probably never seen it. It's this invisible armor that's constantly protecting your data as it flies across the internet. It's called IPsec, and in this explainer, we're going to pull back the curtain and see exactly how it all works.
Yikes! For thousands of years, the stakes for keeping information secret have been, well, incredibly high. Sun Tzu certainly did not mess around. The need to protect secrets isn't new, but man, the battlefield has changed a lot.
Today, that battlefield is the internet. It's this huge public space where our private data travels right alongside billions of other digital messages. So how do we apply those ancient principles of secrecy to this crazy, modern digital world?
Well, for a lot of us, the answer is a VPN, right? We fire it up when we're working from a coffee shop, browsing on public Wi-Fi, or connecting to the office. We just trust it to create this private, encrypted tunnel for our data right through the middle of the public internet.
But have you ever stopped to wonder what's actually going on under the hood? What's the real magic, the actual technology that builds and secures that private tunnel? Well, that's exactly what we're about to uncover. So let's get right into it. The tech that powers so many of these secure connections is IPsec. It's pretty much the unsung hero of internet privacy.
See, IPsec isn't some app you install. It's a framework that works way down at a much lower level of the internet, the IP layer. Think of the IP layer as the global postal service of the internet. You know, its job is to address and send all the packets. IPsec basically adds a layer of invisible armor to those packets before they even leave the post office. So, how does this armor work? Well, it provides three absolutely critical services. First, authentication. This proves the data's actually from the right sender and nobody's messed with it in transit. Then, confidentiality. This scrambles the data so eavesdroppers can't read it. And finally, key management, which handles the super tricky business of securely creating and sharing the secret keys you need to do all that scrambling.
Now this is where it gets really interesting. IPsec can put on its armor in two fundamentally different ways, all depending on what exactly needs protecting. We call these transport mode and tunnel mode.
Okay, this comparison is crucial. In transport mode, IPsec only protects the packet's payload, the actual data. The original address info, the IP header, is left out in the open. The best analogy is an armored truck carrying gold. You can see where the truck is coming from and where it's going, but you have no idea what's inside. This is perfect for direct communication between two computers. Tunnel mode, on the other hand, well, that's like taking that entire armored truck and putting it inside a second, even bigger, totally unmarked armored truck. It encrypts the whole original packet, header, data, everything, and slaps a brand new header on the outside. Nobody can see the original source or the final destination, and that is the mode that powers most VPNs. And you can really see the difference here. With transport mode, just the data payload itself is fully hidden. But in tunnel mode, the entire original packet, we're talking the data and all its addressing info, is protected. This is why tunnel mode is such a powerhouse for VPNs. It doesn't just hide what you're sending, it hides where you're sending it.
So, IPsec has all these powerful tools, but how does it decide when to use them? I mean, it doesn't just blindly encrypt everything that comes its way. It follows a really strict set of rules, kind of like a playbook. I mean, just imagine a huge, busy server handling traffic for thousands of different people. How in the world does its IPsec system know that a packet heading to the company's accounting server needs heavy-duty encryption, but a packet going to a public news website doesn't need any at all? The answer is in two critical databases. First, you've got the Security Policy Database, the SPD. This acts like the team's rulebook. It tells IPsec what to do with all the different types of traffic. Then you have the Security Association Database, or SAD, which holds all the specific contracts for every secure conversation. And that brings us to this core concept, a security association, or SA. Just think of an SA as a very strict, one-way security contract. It defines every single rule for that connection, which encryption algorithm to use, the exact keys, even how long those keys are good for. And because it's one way, a normal back-and-forth conversation actually needs two SAs, one for each direction. So let's just follow a packet for a second. First, IPsec checks the rulebook, the SPD. The rule tells it what to do, either bypass security and send it as is, discard the packet completely, or protect it. If the answer is protect, it then looks up the specific security contract for that destination in the asset. And finally, it uses the rules from that contract to apply the armor and sends the protected packet on its way. Okay, we've covered how IPsec protects data and how it decides what data to protect, but there's a huge piece of the puzzle missing. How do two computers create one of these secret security contracts in the first place, especially when they have to do it over the totally insecure public internet?
This is the classic chicken and egg problem of cryptography, right? To talk securely, you need a secret key. But to share that secret key, you need a secure way to talk. So how do you even get started?
Well, they use a protocol called the Internet Key Exchange, or IKE. The best way to think about IKE is as a highly sophisticated and incredibly secure secret handshake. It lets two parties who know nothing about each other securely agree on a shared secret key, even if an attacker is listening to their entire conversation. And believe me, this is no ordinary handshake. IKE uses clever digital cookies to stop denial of service attacks. It uses a brilliant piece of math called Diffie-Hellman to create a shared secret right out in the open. It uses random numbers called nonces to make sure every handshake is unique and can't be copied and replayed by an attacker. And most importantly, it authenticates both sides to make sure you're not shaking hands with an imposter.
Okay, wow, we have been deep in the technical weeds. So let's zoom back out and take a look at the big picture. Why has IPsec become such a fundamental, foundational part of internet security?
Well, the benefits are just immense. Because it works down to the IP layer, it's totally transparent to your apps. Your email client, your web browser, they have no idea it's even there. That makes it super easy to roll out. When you build it into a router or firewall, it creates a powerful security perimeter for a whole company. It's also transparent to users, and it's incredibly flexible. It can secure everything from one person working from home to the traffic between two massive corporate data centers. And this is where you actually see IPsec in action every single day. It's the backbone of corporate VPNs that connect all the branch offices. It's what's securing your connection when you're working from home. It's used to build secure data links between business partners. It even adds another critical layer of security to e-commerce. So yeah, while it might be completely invisible to us, IPsec is one of the most important protocols working behind the scenes. It's really the foundation of trust and privacy that makes the modern, secure internet that we all rely on even possible. From ancient battlefields all the way to the digital age, the need for security is just a constant. IPsec is today's state-of-the-art armor, but as threats get more and more sophisticated and our world gets even more connected, it really makes you wonder, what's the next generation of invisible armor going to look like? And what new challenges will it have to face?